Today I'm going to show you how to load and search for a spectrum from the database. You might notice some changes. I've done a lot of updates to the user interface and compartmentalized a lot of the code and added some extra features. If you've already downloaded this, you might see some new stuff, so you might want to check out the updates. So with the newest versions of RamanLab, you can check for updates. You just go up here, check for updates, and it'll show you what version you have. I'm at version 1.0.5, which is the latest version as of this taping. If you had an older version, it would automatically start downloading it. You can also do manual ones, and I can show you how to do that in the forum. If you ever have any questions, though, I've also added a new user forum. So you can go up to Help User Forum, and what this will do is it'll pop up the website for the user forum. So right now there's only 2 people. It's me and Olivine. We're just hanging out together here, so please join the conversation. There's lots of things to report. I look at this every day. I get notifications. I'll try to respond as fast as I can. And also, if you have any data file imports that you'd like to be able for your software to for this software to be able to read without you having to do a lot of conversions, just shoot me an example data file and I'll get that implemented. All right, let's close this. Let's go back to RamanLab. So first thing we have to do is import a spectrum. So I'm going to import something from my desktop. It's going to be this file, which clearly is known at this point. And this is what it looks like. There's a bit of a background. This is actually a multi-phase sample. There's a bit of corundum in there, which is my internal standard. But yeah, we move on. And going to select process. Here we can select different types of background subtraction. My favorite is the asymmetrically squares. And you can play around with this and it'll update the screen with a live update to show you the different background parameters. It also has a generate background options. If you click on that, it'll tell you that there's 6 background options, and you can select from this select option dropdown. So there's this conservative one. There's a more moderate one. This one's pretty aggressive. That's a little too aggressive for this sample. There's smooth. That's a little too smooth. A nice balanced one. It's cutting out some of the data here, but that might be fine. We're just doing peak matching. And actually the ALS fast, I think I like that the best. So let's go with that one. So I'm going to apply selected option, and it subtracts it. You can also detect some peaks, although it's not absolutely necessary to do this. You can if you want. This is just doing peak height. It's not doing any proper peak fitting, just for speed and accuracy. Just do some peak fits, and for search match, that's more than enough. If it doesn't come up with ones that you like, you can add your own. You could just click and say, these are my own right here. And just gives you a quick estimate of what the peak position is. You can also apply a smoothing. You could just hit that. That's a pretty mild smooth. If you have really noisy data, it might be useful to do that so you can find some peaks. All right, I'm pretty happy with this setup. I'm going to go to the search tab now. And in the search tab, I've added a lot of options, and it'll all depend on what your sample is like. My favorite so far has been this multi-window approach. The multi-window approach takes a correlation-based method. So if you did correlation, it would just compare the entire spectrum to the entire database spectrum and just go one for one, completely overlap without any weighting schemes at all. The multi-window approach applies a weighting scheme. It breaks up the spectrum into 3 regions: lattice modes, silicates. So the lattice modes would be the lowest, kind of a more bending fingerprint region between 400 and 800 reciprocal wave numbers, and then from 800 on, we're calling that a different region for silicates. And this is really for mineral specific stuff. And then there's the mineral vibration window. This here a little bit more detailed into what vibrational modes it looks at. It looks at a lot of different vibrational modes and tries to optimize it per your spectrum. And we'll get to that. I'll show you that in a second and how it decides on what vibrational modes are. Peak, this one's tough. I put this in here because a lot of people probably use direct peak matching, but it doesn't work that well. I mean, it may work for some cases, but you'll notice when you're playing around with it, it's like this is not very good. And that's because it is looking at just specific peak positions and just optimizing that without really paying attention to the intensity of the peak. Combined does correlation and peak. This is pretty good. It puts more weight into the correlation and it uses the peaks to help sort out certain peaks. And then the last one is dynamic time warping. This one is really good for very difficult spectra, poor signal to noise, lots of shifting of the peaks. It's not good for just if you have a really good spectrum. It takes a long time to run. But if you have a very poor spectrum and you know there's shifts, dynamic time warping is the way to go. I'm going to go back to multi-window. And down below, it gives you a maximum number of results. 10 is the default, but you can add more if you like. Threshold, I'm pretty strict on the threshold, but 0.7 is pretty good. And I put a tip here to remind you, hey, multi-window is probably the best for most cases. And all you have to do now is just press search. And it'll take a few seconds. And then after it's done loading, it'll pop up a new window and I'll show you the results. So on the top left over here is the total results. This one's really good because the answer is hilarite. And there's only 2 spectra of hilarite in the database. But then there's George Chowite, which is very much related to hilarite. And then all these other ones, gaydonite and so on, are all related chemically with each other. And you can click on each one and it'll show you the difference. That one's not very good, but I told it to give me back 10 and it gave me back 9 that it thought it was the best. We can also look at the metadata. This will pop up here and you can look at all the metadata that I grabbed from the rough database. Rough database number, the status of it, the description of it, who acquired it or who sent it into rough, where it's from, idealized chemical composition, just tons and tons of information here. Let's close that out. Oh, and if you wanted to like flip through each one of these specimens, it'll pop up and automatically open up. As long as you have the view metadata window open, it'll just automatically pop up with the next one. Let's go back to the top search. And the red spectrum is the match from the database. The blue spectrum is the data that we imported. The green one up here is the difference between the match and the imported. Just give you a sense of like where there are major differences. Maybe you can search on peak positions of major ones. Here's the corundum peak at 417, 420. And then down below is something interesting that I'm beginning to implement is where common vibrational modes of these different mineral groups tend to occur. So here are some silicate bends, some more silicate bend structures. Here are the silicate stretches way out here. And you notice that the silicate chemistry line item has an overall average fit of 0.86. That'd be a correlation index. 0.99 would be this for this 3-membered ring breathing frequency. I know that because I study hilarite a lot. And then other ones. And these are all pretty green. So it would be a nice fit. And when we do the mineral vibration search analysis, this is what it's using as a basis for trying to fit a spectrum correctly. It looks at all the different modes and tries to optimize what fit works the best. Carbonates, there's a little bit of carbonate there. You can see it's not very intense. And then out here, there's pretty much nothing. And so there's these, arsenate, there's no arsenate there, and so on. So you can look at these as a guide. I wouldn't use these as the absolute truth. These are numbers I put in for vibrational range, and I'm still trying to optimize all these different vibrational ranges themselves. And later on in the code, later on in the software, I'll show you how you can do that and make these numbers a lot better using cluster analysis. And so right now we're basically done. The answer is Hilarite. There's a good fit, and we can move on. There's some normalized intensity options that changes how data is normalized, but and it depends on the spectrum, of course. You can save this. Click on the save button up here. You can save it as anything. I like saving everything as PDF because that's a vector format, and you can always export it as a PNG later on. That would be my option to go to, just so that I have vectors installed, or is vector saved. All right, just as an example, we can go to correlation and then do the search. This is going to be the fastest method. And again, we get Hilarites, but there's some other strange ones that come in, you know, things that match pretty closely, but you know, this is, let's see what's the chemical composition of this. This is a titanate compound, so not too different than Hilarite. But the results are still quite good. They're quite nice and very reasonable. Let's check the mineral vibration one, see what we get. This one will take a little bit longer because there's more things that it has to try and match. And if you see spinning pinwheel, that's good. Again, top two, Hilarite, George Chowite, and a few other things that might be of interest. Again, it's a different kind of searching algorithm, so it's going to give you different results back. Just for fun, we'll take a look at the peak. This should be quite horrible because I have some of the impurity phases listed as peak options. And we got Bragite, polyurethane. Again, it's just looking at peak positions. It is taking nothing else into account besides peak position. So you're going to get some strange results. And this is just the nature of the peak position search problem. A combined, let's take a look and see how that does. So this is doing correlation based and peak position based. And it takes a little bit longer because it's doing two algorithms at the same time. Again, completely different results. And none of these are right. I may have one that's kind of close down at the very bottom, but really it's not very good. And the dynamic time warping, this I'll let you play with on your own because it does take 20 seconds or so to launch. Let me do correlation again so you can see the search results information that's populated down here. This is all good. Close that window, and then here are, if you want to export this, you can copy and paste this information of the top three results, or you can export, or you can save the data in other ways. There is something I'm developing as a launch mixed mineral analysis button. This is still very much beta. It gives you a little bit of information about what it's going to do when it loads. And it's, I'm not done with it. This is just the beginnings of it, but I'm happy to take, if you have any comments or such, I'm happy to describe what it does, or happy to try and implement something that's a little bit better. First thing it's going to do is remove background. It's going to smooth the spectrum. It's going to normalize the intensity between our spectrum and the spectrum from the database. Fitting options, it's going to try to fit the peaks using some of these functions. We'll just use pseudo void because why not? We could do Lorentzian if you wanted to. That's a pretty common one for Raman spectroscopy. Use some physiochemical constraints, so it's going to use some multi-window fitting, and it's going to do an iterative refinement. So we're just going to run this, and it will come back with some answers. I'm still working on the user interface of this, so please pardon it. And we get a Hilarite to come up with. That's great. So I'm going to confirm that one. Eventually this window is going to be bigger down here so you can see the options. But there's, it's a lot of good options to choose from. Confirm gives you an estimated abundance. And this is where it's not working just yet. It's going to fit the data. Then it come up with a residual plot. And then it's supposed to search on the residual for what the next phases are. And this is the part that's really quite difficult to implement, and it's taken me a long time to work out. There's a progress bar down on the bottom left. But based on how I collected the data, 80% hilarite seems to be quite reasonable. 20% corundum would be, also reasonable as well. But you'll notice there's no Raman cross sections in here. This is going to be implemented later on, so we can put in Raman cross sectional data for how efficient materials scatter. That's all to be coming. It's going to take me some time to do. And I'm also working on the speed of which this runs, because it does take a bit of time. But you can play around with it. There it goes. You can play around with it. So when it searches on the residual, it's going to use the DWT method, the dynamic time warping method, because we're subtracting out the measured spectra from the calculated spectra, measured spectra from the fitted spectra, and searching on the residual. And when you do that, the peaks have an apparent shift because you're removing spectral information. And so the peak shapes are going to be cut off. The data is going to be kind of weird looking. And so you need a different method to be able to search. And dynamic time warping is really good at that. Yeah, so anyway, this is a work in progress. It's getting closer, but it's still a work in progress. And now there are some options for advanced matching. So if you go here, it's very similar to the the basic matching. The first thing you get to choose from is what kind of searching you're going to be doing. So this is important. You want to make sure that whatever search algorithm that you're going to be using matches what you want to do down below. And you can mix and match these things. So there's peak specific matching. So we can just search the 520 peak if we wanted to, and then add 417, or we could just search for the 417. I know that's corundum. We can search based on chemical family. I'll talk about this in the database. This is the user implemented filtration. So I have one specifically for plastics, but you can make one for zeolites. You can make one for olivines. You can make one for the plagioclase series if you wanted to. You can add whatever you want to the chemical family to help the search match procedure. You can also add the Hay classification. I chose Hay because it had a fairly detailed high-level classification system to begin with, like Nickel-Strunz. There's not as many high-level classifications, but it really digs down deep, and so does Hay. But I wanted something just as a top level to have a lot of options. And you can only say only elements, required elements, exclude certain elements. I'm going to say it requires aluminum and oxygen. I should say it require. It's only those, but we'll see what happens. And then you can say advanced search. So it's still searching the entire spectrum, which is unfortunate. A lot of prehnite includes. Let's see if we can get to what we want. So I may have to go to peak correlation and make sure I've got my peak there. And tolerance is a little bit high. Let's take tolerance down to 3, and let's launch. Oh, I don't want to do that. Sorry. I'll do the advanced search. Okay, and then we're getting corundum right here. So again, this is a peak searching one, so it's just returning things that have peaks, things that have aluminum, and things that have oxygen. It should have excluded muscovite because muscovite is not an oxide. This is maybe an issue with the database. Corundum right there, number 3, I didn't see that. And so there's aluminum and phosphorus. Now, let's say I know that there's only aluminum and oxygen there. And we only get corundum back. So this requires this is something that I'm developing, that's something I'm working on, is make sure all the entries in the database are classified appropriately. And I do that programmatically. I don't go one by one and classifying them. I write Python code to automatically do that, and sometimes it finds things that overwrite other things. So it's still a problem. It's still a work in progress. So if you don't find what you like right away, let me know. Send it into the chat on the discussion board, and we'll work through it. It'll get there. But we're just starting this journey, and that's how you do advanced searching.